Okay, so it's my pleasure to introduce Marc Hoyois. Hoyois. Okay. So Motivic, cohomology, and Steenrod operations.
Thank you very much. Thank you for the invitation and coming to the talk. So I hope that everybody will get something out of the talk. So I want to start just by talking about Motivic cohomology. So the setting for this is algebraic geometry. So it means I'm going to look at varieties. So these are the geometric objects defined by vanishing and non-vanishing of polynomial equations. And so, you know, when you look at varieties, you get to choose where the coefficients of these polynomials live. So if you want to think of polynomial equations with complex number coefficients, that's an interesting case to think about. But also, so you could be thinking about coefficients being in a field which is not algebraically closed. And this is, so this brings out some new features because, for example, you get to ask questions like, do my equations have solutions or not? Which is not a question which is relevant if you work over an algebraically closed field. And in fact, you can do, you can go even further and look at equations with polynomial equations with coefficients not even in a field. And the example I have in mind is maybe the coefficients are just integers. So this is also an interesting setting. So now it's basically using number theory or arithmetic. So there are Diophantine equations, equations with integral coefficients, and you're looking for integer solutions to that. And so also the Motivic cohomology is something which is interesting throughout this range of possibilities of geometry. So right, so for instance, if you look at complex varieties, it's especially interesting in that case, and then you get to compare this to singular cohomology, for example. But if you look at varieties where non-algebraically closed field, then this type of cohomology theory is going to be sensitive to questions like, you know, do there exist solutions or not? And it's also especially interested in this arithmetic case, and I'm going to say a few words about this later. Okay, so to try to motivate Motivic cohomology, I don't think that's a very easy task. So I'm going to give a historical timeline leading to the definition of Motivic cohomology. Yeah, so, and I should say Motivic cohomology is one of these things that was that unifies various things, or it was arrived at from different perspectives. So there's more than one, you know, timeline of events that converges to Motivic cohomology. So I'm only going to present one of these timelines for simplicity. You could say this is the K-theory timeline. So let me start in 1957. So at that time, Grothendieck proved his Riemann-Roch theorem. So, so let me recall what this theorem is. So this was a question that Riemann was asking in the 1850s about the number. So if you have a Riemann surface, you want to know how many meromorphic functions are there with prescribed poles and zeros. More precisely, you want to know the dimension of the space of these meromorphic functions. And Riemann and his student Roch answered this question by giving the Riemann-Roch formula. So this was something about complex Riemann surfaces. And so in the early 50s, actually, before that, Hertzberg generalized the Riemann-Roch formula to higher dimensional complex varieties.
Sorry.
Question?
I stole my call.
And so in 1957, Grothendieck proved kind of the ultimate version of the Riemann-Roch theorem, which generalized previous versions in various ways. In particular, one of the generalizations here is that Grothendieck works in purely algebraic settings, which makes sense over abstract fields, and not necessarily just for the complex numbers. So that's one way in which Grothendieck generalized this. So the key kind of new ingredients that he had to introduce to even formulate the statement was K-theory. So what is this? So X, so let this be a variety. And K0 of X. And so, I mean, back then it was just called K of X, but now it's called K0. That's a bit of a spoiler. But this is an abelian group. And it's fairly easy to define. So you just look at the free abelian group. On symbols brackets V, where V is a vector bundle on X. And then you add some relations, namely, so we say that V is equal to V prime plus V double prime if whenever there is a short exact sequence of vector bundles. So with V in the middle we have subbundle of V prime, and the quotient is V double prime. So this is what K0 over variety is. So very shortly after this, so you see if you look at this definition, this is something that could make sense in many other geometric contexts. And in fact, Atiyah and Hirzebruch in 1959, they define, so Atiyah and Hirzebruch, so they just imitate Grothendieck's definition, but when X is now a topological space, so they define K0. So I'm going to write top here. This is not standard notation, but it's just to distinguish it from the algebraic one. So K0 top of X, so now X is a topological space. It's also a group defined in exactly the same way, where you look at complex vector bundles in the space. The reason that they did this is because they also, they actually got a Riemann-Roch theorem for differentiable manifolds using this. Right, and there's some sort of miracle that happened at this time in the history of mathematics, is that at exactly the same time as all these things are happening, Bott proves what is now called Bott periodicity. Which is something which a priori has nothing to do with any of this. So this is so Bott proves that the homotopy groups of the infinite complex unitary group, there's a 2 periodicity in the homotopy groups. So by combining this K0 construction and Bott periodicity, then Atiyah and Hirzebruch were able to extend this abelian group to a whole graded cohomology theory. so this is a TI tensor group that they defined, they were able to define K star top of X. And so star is could be any integer, and this was a generalized cohomology. So that means that this thing satisfies all the axioms that ordinary cohomology satisfies, except that if I plug in a point here, I don't just get Z, I get something more complicated. But that's the only difference. And so yeah, so this is great because if you have a generalized cohomology theory, then you can actually compute this thing by, if I give you a space, you can break up the space in small parts and compute the cohomology theory this way. So if I have an open covering by two opens and the intersection, then I will get a long exact sequence which relates these groups. And it's not something that I can even consider if I only know K0. So one of the things that you get by having a generalized cohomology theory, and by the way, I think this was historically the first example of a generalized cohomology theory that people considered. There's been many more since then. So one thing that you get is the spectra sequence. So now it's called the ATIA Hitzenberg spectra sequence. So it's a spectral sequence that you can use to compute this K theory. So the first page of the spectral sequence has just ordinary cohomology of X with coefficients in the K theory of the point. Right, and this thing, in that case, is very simple. It's just a Laurent polynomial ring in one variable. One variable in dB2. Okay, so this was, this is an extremely powerful computational tool. And so because of this plot periodicity result, basically, this K theory just kind of exploded in topology. Like, people were able to do tons of computations and prove lots of theorems using this new invariant. Whereas in algebraic geometry, well, we still only had this K0 group, and there's not much that we could do. So yeah, so at this time, people were hoping to reproduce this kind of success of K theory in algebraic geometry. So people were looking for ways to define higher K theory groups for, so K sub n for other values of n. That would be something like a generalized cohomology theory for algebraic varieties. So it took a while for this to happen. So there was some progress in between. So Bass defined K1 of varieties, and then Milnor defined K2. And these three things, these three groups fit together as you would expect from a generalized cohomology theory. You had some exact sequences and things like that. But it wasn't until 1973 when Quillen defined Kn of X for all n. Right, so he gave a uniform definition of all these higher K theory groups. And proved a lot of things about them, lots of properties, and made a lot of computations, such as he completely computed these K theory groups when X is a finite field, right, so that means you look at varieties over finite fields and just the point there. He computed the K-theory of that. Yeah, and he got the field medal for this in a few years later. So that was a big deal. But there was still, so topology still had an advantage in that they had this spectral sequence for ordinary cohomology. And this was still missing in this algebra geometry picture. What about the Atiyah-Hirzberg spectral sequence? So what we wanted was to have a spectral sequence converging to these higher K-theory groups, which, I mean, are extremely difficult to compute. Because, but the problem is that we didn't know what fits here. So there was no analog. So K-theory is an algebraic analog of this thing, but there was no analog of this part, of ordinary cohomology in algebraic geometry. So there were lots of speculation and conjectures, and what conjecturally would fit here was called Motivic cohomology. So in the early 80s, there were lots of conjectures that were made by, mostly by Beilinson, also by Lichtenbaum. They made really bold conjectures concerning the existence of properties of this mysterious cohomology theory, and how it relates to various other things, in number theory and elsewhere. This was finally defined by Brook in '86. So Brook defines Motivic cohomology. Well, he didn't call it Motivic cohomology because he didn't prove all these conjectures that were associated with it. So it was just a kind of a candidate for Motivic cohomology, and the name that so he was calling it higher child groups. Okay. So in a moment I will give you an idea of the definition of Brook's definition of Motivic cohomology. It's a fairly elementary construction. Okay, so Brook defined this. He proved several things. He was not able to obtain this Atiyah-Hirzberg spectral sequence, though. But yeah, actually, this still took a long time. And at the end of the 90s, basically, the work of many people finally, it was proved that. So this Atiyah-Hirzberg spectral sequence was constructed going from Brook's higher child groups to higher algebraic K theory. So let me give some names of. Yeah, so roughly at this time, so Brook, Lichtenbaum, Friedlander, Suslin, and Levine. So they construct the Atiyah-Hirzberg spectral sequence for algebraic varieties. Okay, so this is the end of my timeline. So So basically, nowadays we have a very well behaved definition of Motivic cohomology, and it's been very successful in proving many things and solving conjectures. So let me mention probably the most famous one, which is the Brocato Conjecture, that was proved, whose proof was completed 5 years ago by Voevodsky. So
you said it has some kind of applications to varieties. Can you give an example?
Of application
To structure varieties or something, or to field varieties.
Well, I mean, the Brocato conjecture comes to mind, obviously, but
Well, no, can you state an example of application?
You could state that if you want.
Yeah. Or is this some kind of, or is this thing just some kind of closed thing all in itself, just developing theory for the sake of theory?
is it? No, definitely not. No. So, yeah, sorry. I mean, yeah. The only thing that comes to mind now is the Brocato conjecture. I know there are more elementary things that just don't come to mind right now. But the Brocato conjecture is a statement which, it's a statement which does not involve anything that appears on the board here. So it's a statement about. It gives a presentation of. It's a computation of the Galois cohomology of fields.
Or what?
Of fields. Galois cohomology of fields. So should I write that?
Let's say something about varieties.
I think you should give the talk you meant to give.
Yeah, I mean,
So there's no obvious geometric applications.
So let's just
I
listen
mean,
to
they
the
are.
talk.
They are.
Just keep on going.
Yeah, I mean.
Well, I think I asked a reasonable question.
Okay, so he's not answering.
Well, tomorrow we're having a 2-hour follow-up between 12:30 and 2:30. It's advertised. Do you want to come?
What?
Do you want to come? I invite you to come.
Thank you. We'll see.
Okay, 12:30 and math 1:30.
Yeah, sorry. So just because I cannot answer your question doesn't mean that there's no answer. And I know there is an answer. So there's many applications to geometry. But maybe not all of them are necessarily very elementary. So it's. So something I might talk about tomorrow, for instance, is the classification of vector bundles on surfaces, or these kind of things. So this is something, these are very recent results which uses some of this machinery, for example. Right. So let me give you an idea of what these higher char groups are. Right, so first, let me tell you about the ordinary char groups. So X is going to be a variety here. The group of the cycles on X so this is the definition of this word. So this is denoted Z of X, and it's a free abelian group on closed subvarieties of X. Just a combination of subvarieties. So the star here, this is a grading because this thing is a grading group by the codimension of the subvariety. So I'm going to describe an equivalence relation on this group and take the quotient. One reason to consider this equivalence relation is that you'd really like this thing to be a graded ring where the product would be given by intersection of these subvarieties. But this, if you just look at this thing, this doesn't work because the intersection of two subvarieties, given codimension, the codimension of the intersection may not be the sum of the codimensions if they intersect in a bad way. So to fix this, we're going to introduce an equivalence relation here, and this is a rational equivalence. So a rational equivalence between two cycles. Alpha and beta on X. So the idea is that this is a family of cycles that interpolates between alpha and beta, and is parametrized. It's just a one-parameter family, so it's parametrized by the affine line. So more precisely, rational equivalence is a cycle gamma on X product with the affine line. And it's such that if I intersect it with the fiber over 0, I get alpha. And if I intersect it with the fiber over 1, I get beta. And so then the char groups, these are defined as I look at this group of cycles and I quotient by the equivalence, by a rational equivalence. And now this thing is actually a commutative ring where the product is given by intersection, when it makes sense. Right, so what are the higher char groups? So these ordinary char groups are the things that appear in the Riemann-Roch theorem. So the Riemann-Roch theorem relates, it's about the relation between K0 and these char groups. So the higher char groups are supposed to be related to the higher K3 groups in the same way that the classical char groups here are related to K0 via the Chern character. And the ID, so the ID is quite simple. From a point of view of homotopy theory, when you quotient something by an equivalence relation like this, what you're usually doing is you're actually considering the connected component of some space. And so what is the space going to be in this example? So you could imagine that you had some space where the points of this space are these algebraic cycles, and a gamma like this, I think of it as a path in that space from alpha to beta. But then I can also have homotopies between paths, right? And what would this mean in this context? I mean, I could have a cycle which lives on X cross A2, which restricts to two of these gammas on the boundary. So there'd be a homotopies between the paths, and I have higher homotopies and so on. So I can build the whole space this way, and the connected components pi 0 of this space is exactly these char groups. So then Bloch's idea was to say, well, the higher char groups are going to be the higher homotopy groups of that space. So, yeah.
Is this a bi-graded group or something? It's like
Yeah, it's right. It's bi-graded because, right, in some sense, the space itself is graded by this codimension. Yeah. So now to make this precise, okay, when I say space, what you actually get this way, if you proceed kind of as I explained, you're gonna get like a simplicial set or a cubical set, depending on how you set things up. And this is a kind of combinatorial of things, which has homotopy groups. So the idea is that this is pi 0 of the space of cycles on X, and then the higher child groups X, I. So this is a Brock's notation. So this is the ith homotopy group of that space.
Meaning that homotopies come from additional affine lines?
Yes. Right. So the
topological homotopy is rational.
Right. Exactly. So. Yeah, all the high homotopies. So if you're wondering, you're going to build a simplicial set whose nth term is cycles on X times an, and you have to define the boundary maps given by these intersections with various faces and so on. Yeah.
And then it is the ordinary topological homotopy groups of that simplicial space, right?
Yeah.
Yeah.
Just
it's the ordinary homotopy groups of a construction.
Yeah.
Of the simplicial object out of this cycle.
Yes. So.
What do you get for Riemann surface?
Sorry?
What do you get for Riemann surface in this case?
What do you get
What are
for
the
a
higher
Riemann
child groups
surface?
for Riemann surface?
Oh, okay.
It's asking
So,
what do you get for a Riemann surface in this case?
yeah. Right. So these bi-graded groups are unfortunately uncomputable. I mean, there's not a single X that I can give where I can give a complete answer. And I mean the reason. So yeah.
What about the first one?
Sorry.
What about CH1?
So let's see some examples. So when star is 1 here, so these are codimension 1, so these are just divisors on X. And this, so CH1, CH1 is just the divisor class group. And this is, so it turns out this is the same as the group of line bundles on X.
So this is just pi 0, right?
Yeah, so pi 0, yeah. Right. So
what about pi 1?
Yeah. So in that case, okay, great. So in that case, the space of codimension 1 cycles on X is the same as the space of line bundles. And if you think of so pi 0 of that space is just this CH1, and what you think what the pi 1 of that space would be, they're going to be what automorphism of a given line bundle are. And this, so CH 1x, 1, this is going to be, so automorphism of line bundle, it's an invertible function on X. This is just invertible function.
So if you take I, and it's just these line bundles.
If you take, sorry.
So this is basically like the scene check homology or 1.
Yeah, right.
So what if you take I equals to 2?
Then I equals to 2, then there's going to be 0 beyond that. Yeah. There's only 0 and 1 in that case, when you have 1 here. Yeah. So there's only these two. There's the isomorphous classes of line bundles and this one.
For Riemann surface is the actual known.
So yeah, so CH1, yeah, it's in some sense completely known. It's always this thing. But this illustrates something. I mean, so you see that if you work with the complex numbers, then this as an abelian group is a huge abelian group, which is not is not finitely generated. It's not, it's uncountably generated at even group. And this is because the field of complex numbers is a huge field from an algebraic perspective. So this Motivic homology group, at least in some range, such as here, then they see this kind of thing, and so you can, well, so they're not finitely generated at even group, so you can't really hope to. It's not clear what it means to compute them, right? Because they're just really large groups. So even if X is a point, for instance, we don't know, we don't know what the Hoyois groups are. But in some sense, we shouldn't hope that we can know what they are. Okay, so let me introduce an alternative notation. So this is the Hoyois notation, and this is also denoted H. Okay, now I'm going to get confused. 2n minus I x zn. Yeah, so it's just another notation for this, but this looks more like you're taking the cohomology of X with coefficients in something.
And what does Zn mean?
So Zn, so this is Zn, there's actually a chain complex Zn whose cohomology gives you this. So that's what this means.
Oh.
But you could just take this as the definition of this alternative notation. Okay, so maybe, So let me say one more thing about Motivic homology in the case, in a more arithmetic context. So now I want to look at my X is not going to be a variety over a field, it's going to be a variety over the integers. So that means I give myself a finite number of polynomial equations with integer coefficients. So everything I talked about makes sense in that context. So you have Hoyois groups as defined, a Motivic homology which is defined for this. So in this context, we also have the Zeta function of X. So this is it's a function of a complex argument defined as this Euler product over all the closed points of X. So this means solutions of these equations over a finite field. And then take 1 over 1 minus the cardinality of so this is the field in which, sorry, that's an X. Right, so this is a residue field at X. That means that's the field where the solution, the finite field where the solution is defined to the minus X. Okay. So it's not too difficult to see that this is, so this product converges, it's a countable product. It converges when the real part of S is greater than the dimension of X.
So when X is Z, you're just getting this classical. X is spec Z, you're just getting classical.
Right, so if X is spec Z, which means I look at an empty set of equations in 0 variables, then this is the classical Zeta function. And more generally, if X is the spectrum of a ring of integers in a number field, and this is a Dedekind Zeta function. So that number field. And conjecturally, this has a meromorphic extension to the whole complex plane, but this is an open polynomial. I mean, we know it for the usual Zeta functions, but not in general. Okay, so this is conjecturally closely related to Motivic cohomology. And so let me mention the conjecture of Soulé to give you an idea of this kind of relationship. And this says that the order of the Zeta function at, so the order of the polar 0 at s is equal to n. So for an integer n, is given, so it's computed as some sort of it's alternating sum of ranks of Motivic homology groups of X. Right. So the n that is here is the same as here.
Sorry, so this one related to that one. It's the lower I.
Oh yeah, sorry. Yeah, so this is Motivic homology, which is a variant. Yeah. If I wanted to put homology here, I'd have to change the indices. So
But you can't get this rank from this rank. It's not something like that.
yeah, so there's
So
going to be a Poincaré duality between homology and cohomology. So it's just the expression becomes more complicated if I use cohomology.
So it's either side computable or just inequality?
Is either side
Actually computable or is just inequality? It really shows like the two things are equal as opposed to each one being computed.
Yeah, exactly. So the two things are equal.
But it's not but can either will be computed?
I mean, you could hope to compute this one in some cases, yeah.
But not variance.
Maybe also. Certainly not in general, you can't really hope to compute either side. So you have the rank of this group here. So this depends only on the rational vector space associated with this. So something I did not mention is that this T-Harrisburg spectral sequence with rational coefficients just becomes an isomorphism. So then there's no difference between K-theory and Motivic homology. So you can think of K-theory and Motivic homology as two different integral structures on this rational vector space. So this means that you could state this conjecture using K-theory, and this is what actually Soulé was doing. But it's reasonable to use Motivic homology instead because, so conjecture, so this tells you something about the order of the Zeta function, but if you actually want to know something about the values of the Zeta function, then this becomes related to the actual integral value to Motivic homology groups, not just their rank, but the order of these groups and so on.
So we checked it for some things. We checked this conjecture for some.
Yeah, so this conjecture is known for number fields, so rings of integers in number fields, for instance. So this is Spectra, the Dedekind Zeta function. It's known also if n is the dimension of x, if n is the dimension of x minus 1, then this conjecture, if you take x to be an elliptic curve, then this conjecture implies the Bird-Trinitz-Dye conjecture, for example. So this is an extremely deep conjecture, which right. But I just wanted to mention kind of this point of view. So there's some sense in which Motivic homology is kind of a calibreification of the Zeta function. That's one way that you can think about it if you're inclined towards number theory. Okay. So I'm going to move on to talking about Steenrod operations in topology, so this is going to be completely independent of that. So are there any questions on this part? So this is in topology. All right, so what are we looking at here? So say R is a commutative ring. So if I have a space X, then I can look at the cohomology of X with coefficients in R. And this has, so let me point out two features that this has. So the first one is that if I have a map, I have a continuous map from Y to X, then I get a pullback on cohomology. Right. So it's functorial in the space. And I also, another thing that we have are suspension isomorphisms. So the cohomology of X is the same as the cohomology of the suspension of X, but shifted by 1. So what do we mean when we talk about operations in cohomology? So let me write A n sub R for each one. This is a set of operations, so maps from the cohomology of a space to the cohomology when shifted by n. So I look at degree n operations like this are compatible with these two features. So compatible with 1 and 2. And if I put all the n's together, what I get is actually a graded algebra. And the multiplicative structure is because I can compose such operations. This is crazy. All right. Okay, so why do you care about this algebra? Well, it depends on R, but so this algebra could be just R itself, in which case it would not be very interesting. But if it's a complicated algebra, then by definition of this, because these elements here act on cohomology of spaces, right? So the cohomology of any space is actually a module over this algebra. And if you have any map between spaces, then this pullback map is linear for the action of this algebra. So this potentially can put a lot of restrictions on what cohomology of spaces can be and what maps between cohomology groups induced by maps of spaces can be. And so this is extremely powerful for computations to have restrictions like this. So right, so that's in theory. This is it'd be a nice thing to have. Now, can we actually say something about this algebra in some cases? And the answer is yes. So what about if I look at cohomology with rational coefficients? So unfortunately, in that case, the answer is that this is just Q. So in other words, the only operations that exist in a rational cohomology is just multiply by a rational number. So we're not going to get anything interesting by considering this in that case. Okay. The next thing you can ask is what if I consider cohomology with integer coefficients? So if it's got to be interesting in some case, it better be interesting in that case. And this actually is very interesting, but it's complicated. So it's too complicated to write down. Now that's not really true. If you really wanted to write it down, you could do it. But there's not much incentive to do that. So the one which is kind of hits the right balance between usefulness and computability is when I look at coefficients in a finite field, Z mod P. So P is prime. And this is what Steenrod is. So let me just state the theorem about this. So this thing is completely understood. It's a finite dimensional vector space in every degree, although it's not finitely generated as an algebra. So this is a computation of Serre and Charton. So that they compute this algebra. Okay. So I can't exactly tell you what it is. But let me just give you an idea. So it's generated by some particular operations that you define by hand. So one of them is called beta, is the Brockstein operation. And then you have operations p to the I, which are power operations. So these brackets here means free non-commutative algebra generated by this. So I don't know what the standard notation is. And then you have some explicit relations called the Adam relations. Between this and everything is completely explicit. So this was so this was done, I guess, in the 50s, and it had a huge impact on various problems in topology that people were not able to solve because they lacked the computational tools. So let me mention some applications of this. I don't know if it's fair to call these things applications. They're more like, because they use not only this, but also other things. But these are problems that reduce to computations is cohomology, which people did not know how to do until this was done. So
You have 5 minutes.
yeah, thank you. So let me mention, so one problem that was solved using this is the problem of computing the maximum number of linearly independent vector fields on sphere. So I think this was done by Milner. And what else? So we have the proof that you only have real division algebras in dimensions 1, 2, 4, and 8. The first proof of this was done using these cohomology operations. Nowadays, people usually teach a different proof using topological K-theory, which is a bit simpler. So classification of smooth manifolds. Compact, smooth compact manifolds up to supported. So you can completely classify these things. And, this is really, yeah. This one is really, you could say, is almost a direct application of this result. Okay, and there's more. But, okay, so in the few minutes I have remaining, let me tell you about now the Motivic version of this story. So we can consider, so we're going to consider the exact same way operations of the Motivic homology of varieties, and now this is going to be some bi-graded algebra. Okay, so let me just write a Motivic Z mod P. So it's defined in a similar way as before, but now we use Motivic homology instead of singular homology. So it's a bi-graded algebra. And we'd like to compute it. So let me state the theorem. So Voevodsky and myself, Shane Kelly, and Paul Arneus and so the answer, kind of surprisingly, is that this algebra is essentially the same as in topology. So it looks like the topological Steenrod algebra, and then okay, you have to change scalars to the Motivic homology of the base field. There's one difference between topology and this setting is that here the point, which is the base field, has non-trivial cohomology. And this cohomology acts on the cohomology of anything else, so that's why you have this term. So a crucial assumption here is that the characteristic of that field is not equal. So Voevodsky proved this when the characteristic of K is 0. And the reason that he couldn't prove it more generally is that he was using, he was basically using the analytic topology or the complex numbers to compare directly with topology, and he was also using resolution of singularities, which is not something that we know that we have in positive vectors.
What about over Z?
Sorry?
And what about over Z? Is there something like this over Z?
When K is Z?
No. Instead of ZP.
This is Z?
No, instead, yeah.
Yes.
Is there a statement like this?
He's asking, the case that was so complicated in the topology case.
No, but it was. He said it was known in the topology case.
No,
Yeah.
Z, Well,
I mean,
set up.
You do see.
yeah, I think. I mean, I think you could use. You could probably compute it, but it's.
No, but does this hold if you replace dp by?
It should. Yeah, it should hold this.
But you didn't finish telling us
100% sure.
how you do it in Z mod P instead of over the analytic topology. You were saying what Voevodsky did, but then.
Right. So, so if the field has characteristic P, then you have to use substitutes for these characteristic zero facts.
You mean characteristic, finite characteristic not P?
Finite characteristic not P, yeah. So then, for instance, we use the Untitled topology instead of the analytic topology. And then, well, resolution of singularities, you don't have it, so you have to use some weaker results that suffice, like these results of Gabor on and de Jong and Gabor on alterations and things like that. Okay, so let me make one final comment about this. It'd be extremely desirable to have a result like this when the characteristic is also equal to P. There's several reasons for this, but one reason is that so a result like this, so I told you before that Motivic homology is especially interesting in this arithmetic setting where you look just at Dirichlet-Time equations. If we knew this result without this assumption, then we could globalize this from fields to, for instance, to the integers. So then we would have the Steenrod operations for Motivic homology of things over the integers, and so this is a kind of computational tools that would be really useful in that context. But now, of course, because no given prime is invertible in Z, then this is currently an obstruction to doing this kind of globalization. Okay, so I'll stop here. Thank you.
So here you mentioned all these applications of the Steenrod operations. Are there any related things that you could get from this theorem?
No, I don't think there's any application. I don't think any of these in particular, as far as I know, has an analog in that setting.
You couldn't just plug in what you did for the cobordism thing and see what it spits out?
I mean, some people are hoping that you can do that, but there's obstructions, like there's other obstructions to copying the topological proof. In particular, understanding what optical cobordism means and these kinds of things.
Do you know if there are any applications yet, or is it too?
Well,
so
this is one thing. In topology, you're usually using the Steenrod algebra mod, like at 2. You're using at the prime 2. You're using the 2 primes together. Exactly where the power comes is exactly what's excluded, I think. In this more difficult.
Well, I mean, but in some sense, topology is always characteristic zero, right? If you try to compare, right, with algebraic geometry. So, so applications of this. So this was, this was a really key ingredient to the proof of the Brocato Conjecture, for instance, in Voevodsky's proof of the Brocato Conjecture. And I mean, people have used it, in the same. So I said, if you have this algebra, it puts a lot of restrictions on what homology of things can be. So it's just, you'd hope that it's useful for many computations, and this turns out to be the case. So there's many computations for Motivic homology of various things that we use these Steenrod operations in various ways.
He used it for his results, before your results. What about your results?
Yeah. Yeah, because the proof of the Brocato conjecture can be, if you know it in characteristic 0, you know it everywhere. So that's he only needed this in characteristic 0.
Has it been done in other characteristics?
Yeah, so Brocato conjecture holds. Yeah, it holds in all characteristics, but you can kind of easily reduce to the characteristic 0 case kind of before you do anything else.
So anyway, your results are they?
Yeah.
Why I don't know.
So what's the year of your result? What year is it?
Oh.
Voevodsky's is earlier, right?
Yeah. So this is maybe 2010.
What?
This is 2010, I
Just
think.
write it down.
This. Yeah, roughly. I mean, around that time. I mean, it's yeah. The publication date is gonna be 2017.
So to answer to our same question, there's not been applications that you could relate to us yet?
Right. I don't think so. There have been many applications of this, but most of them have to do with computations. Computations computations happening within this Motivic universe, exactly.
Disconnected from the rest?
Yeah, for now, I mean, yeah.
Doesn't seem easy anyway, so it's going to take some time.
Yeah.
But for instance, would you expect applications, let's say, if this formula held when the characteristic of K was equal to P as well?
Well, I mean, yeah, sure. I mean, I would expect, yeah. I would expect that this would allow many computations for in this arithmetic setting over Z, which are not possible up to now. There's many conjectures in that setting, and I mean most of them seem completely out of reach. But yeah, maybe we can do a little thing here and there.
So, is there anything similar to Adam's spectral sequence to relate this structure to homology theory, homology group of algebraic variety?
Yeah, there is a Motivic Adams spectral sequence. Yeah, exactly. So this is the main computational thing that people are doing with this. So it's a spectral sequence. Yeah. With E2 page is X groups over this algebra. And I mean, topology converges to the stable homotopy groups or something. So this is how people compute stable homotopy groups of spheres, for instance, using the Adams spectral sequence. And yeah, so the same thing is being done here. People are trying to compute stable homotopy groups of algebraic spheres over complex numbers or things like this. And these things are related to lots of kind of interesting algebraic invariants and the theory of quadratic forms and fit groups and these kind of things. Hermitian K-theory. So I don't know. There's lots of computation being done. A lot of it is just data, and you don't really know what it means. So that's
Big data.
big data.
Any other questions?
Could you tell us in 1 minute what you're going to talk about tomorrow? Obviously, it's while we're talking, I mean, summarize too much.
Yeah, so I think it's going to be an introduction to A1 homotopy theory. So in particular, define what that is. And I mean,
A1 means you replace the interval by the affine line.
Right, A1 is this affine line, yeah, and this is kind of, I mean, there's a lot of that that goes into the proofs of results like this, and so this was kind of something that Voevodsky and other people started. And I'll talk about that. And hopefully I will get to some non-trivial theorem, but not sure which one yet. Maybe, I don't know, if people are interested in classification of vector bundles, for instance, I could say something about that.
And we have unlimited time.
Well, he has to go home eventually.
Well, there it is.
Okay, let's thank the speaker.